What is up, you guys? So in this one, we're going to start working with SciPy. And SciPy is a really awesome Python library dedicated for a lot of mathematical purposes, such as integration, special functions. You can do optimization, numerical optimization, from numerical optimization to convex optimization. You've got signal processing as well as linear algebra functionalities. So in this Python series, I'll be dedicating a few extensive lectures on SciPy. So you can first head to the website right here and you can start reading the documentation. So as an introduction, what is SciPy? It's a collection of mathematical algorithms and convenience functions built on the NumPy extension of Python. So for those of you who don't know what NumPy is, it's a library dedicated mainly for matrices and numerical computation. You can head over to their website right here, right? And also, I've got a video on NumPy as well, published almost around a year ago. So for those of you who don't know how to work with NumPy, you can watch this video. I talk about a lot of stuff, including a lot of matrix functionality, types of products, matrix decompositions, including the eigenvalue and the singular value, and a lot of operations you can do on matrices, such as solving a linear system, inverting a matrix, types of inversions, such as the Moore, Penrose, pseudo-inverse. So yeah, a lot of good stuff in this tutorial. So back to SciPy is further decomposed or divided into subpackages. You've got SciPy.cluster, responsible for clustering algorithms in machine learning. You've got some constants such as, h bar in physics, gravitational constant. Do they got the pi? Yeah, just wondering. Anyways, there's a lot of constants here for those of you into physics, differential equations, and a lot of mathematical application and a lot of mathematical stuff really over here. You've got the orders, SI prefixes, right? Starting from the zepto up to the iota. You've got binary prefixes such as kibi, mibi, gibi, right? Some mass units, some angle units as well, degrees, arcman, time units, length, inch, foot, yard, Fermi, pressure units, the atmosphere, psi, area as well, speed, energy. So a lot of stuff over here. This is a very rich package, I think, in my opinion. You also got the FFT pack, responsible for fast Fourier transforms, right? So you've got FFT, IFFT, the inverse FFT. You've got 2D FFT, as well as RFFT. You've got the discrete sine transform, in case you don't know. So discrete sine works in a sine basis. The traditional FFT works in a complex exponential basis. You've also got the discrete cosine, which works in a cosine basis. You've also got pseudo-differential operators, such as the Hilbert transform for periodic signals or sequences. You've got convolutions of signals, so really a lot of FFT stuff going on over here. You've also got the integrate, which is responsible of computing integrations, right? So you've got Simpson's integration, trapezoidal integration, Runge-Kutta or RK, integrations for solving ordinary differential equations, right? You can also solve boundary valued problems as well. So really a lot of packages here. I'm not going to go in depth into each and every one, but I will be doing so in the few coming lectures on Python. Okay, so for now, let's see how to get this into our machine. So let's open a terminal over here and go to the desktop. You can go to any path really, but I'll choose the desktop. I'm going to make a folder that is called Skippy. Simple as that. I'll cd into it, right? To create a Jupyter notebook. So Jupyter notebook. So here's my empty path, and I'm going to create a new Jupyter notebook and call it, because we're going to be talking about functions, I'll call it functions, right? So basic functions of Skippy. So the first thing to make sure of is that if you have Skippy on your machine. Now I have it, no problem. But in case you don't, well, you go back here, you open a new instance of a terminal, right? You type in pip3 install Skippy as such. Now since I have it, it didn't take that much time and it told me requirement already satisfied, right? But if that's not your case, you have to wait a bit so that it downloads. So now that I have it on my machine, I can go ahead and start writing some Skippy code. Now, as we mentioned, Skippy builds on top of NumPy, right? And for all basic array handling needs, you can use NumPy functions. So I might as well import NumPy. So for calling any function in NumPy, all you have to do is just np dot whatever you want, right? And that's how you call functions in NumPy. So NumPy, I'll import it as np, right? And I'll go down here and np dot, for instance, let's say I want the absolute value of -1 and I get a 1, right? That's how you work with internal functions of a library. Now, rather than giving a detailed description of each of these functions, we're going to discuss some of the more useful commands which require a little introduction to use to their full potential. Now, what I mean is that to use some functions with some Skippy modules, all you have to do is, like, from Skippy, if you want to use, like, for example, the integrate module, all you have to do is from skippy.integrate or import skippy.integrate as integrate, for example. And there you go. We have the integrate module, which we could work with. So, for example, let's say I want to compute the integration of a specific function. So this could be accomplished using the quad, right? That we will be talking about in future lectures, but you get the point. In case you want to reference a specific submodule or sublibrary in Skippy, this is the way to do it, right? Now, there's a lot of class instances that make use of, let's say you want a specific, I don't know, let's say you've got the following matrix. So we're concatenating 3 along with 5 zeros, right? So here's my vector, right? Well, with the R command, say np.r, you could do this easily. What I mean is you open brackets as such, type in 3, then 0, 5. Instead of just calling np.concatenate, you can get the job done with the r underscore command, right? This is better for readability, right? Now the R stands for row concatenation, obviously, because if the objects between commas, are 2D arrays, they're just stacked by rows, right? So, and thus the R. Now, if you want to do the stacking by columns, all you have to do is C underscore, right? So C underscore, let's say I have an NP array that is 1, 2, 3, and then I have another array that is 4, 5, 6. As you can see, each row, each array was stacked in the columns of this matrix. If I say R, they're stacked in one row, okay? This is very important. From now on, R is stacking by row and C is stacking by column, right? Now another very, very useful class instance which makes use of extended slicing notation. So what we're doing here is that we're slicing, right? So that's my matrix and I'm slicing it into columns, right? So each input is actually a slice of this bigger matrix. Now you've also got the function that is called the mgrid, and the mgrid is an instance of NumPy which returns a dense mesh grid when indexed. So let me show you what I mean. So np.mgrid, if I tell it 0, 5 and then 0, 3, you can see that I've got, if I return it in, let's say a variable a, and I go ahead and index as 0. Well, what do I see? I see that I have extracted the first matrix, right? And if I go ahead and say A1, I have extracted the second matrix. Now, what are those? Those are matrices that you can generate using, so 0 till 5 explicitly, so 5 is dropped. So this is from 0 till 4. 0, 1, 2, 3, 4. So in total, I've got 5 rows and 3 columns, right? And so this function can be used to construct 1D ranges as a convenient substitute of the other function that is called arrange. Now let's talk about polynomials. When working with SciPy, there's two ways to deal with one-dimensional polynomials. The first one is to use the poly1D class from NumPy. So if we go ahead and from NumPy import poly1D, that stands for polynomial one dimension, you can go ahead and define it as such. So poly1D, let's say 3, 4, 5. I have this polynomial. Well, what is it? You can print it, and it's 3x squared plus 4x plus 5. And the beauty here, I would say, is that you can perform polynomial operations. So let's say you want to multiply two polynomials, p times p. There you have it. So 3x squared times 3x squared is 9x4. Then 3x squared times 4x, that's a 12x cube. And you've got the other 12x cube. Well, that's a 24x cube. And you get the point. So you can expand polynomial operations, right? You can also go ahead and integrate polynomials. So without having to use the integrate sub library of SciPy, you can go ahead and say integrate and say k equals 6. So what we just got here is that we're integrating this guy, right? And we're saying that, oh, in case you get a constant of the indefinite integral, we'll just set it to 6. That's another way of saying when evaluating the integration of this polynomial. So you've got this integration, right? This evaluates to this. But don't forget that this is an indefinite integral. So you've got a c over here. Well, this c is 6. Why? Because I just said, set that constant to 6, right? You can also compute derivatives of polynomials. So print p dot, well, what does derivative start with? It starts with a deriv, and that's it. So you've got to open and close parentheses for this. Well, there you go. So the derivative is 6x plus 4, right? So yeah, this is how we're going to work with polynomials. This is the first way. The other way is to handle polynomials as an array of coefficients with the first element of the array giving the coefficient of the largest or the highest power of the polynomial, right? So the alternative is to work with a polynomial as just an array, right? So I can view this polynomial over here as just 3, 4, or 5. That's a polynomial, right? So in case I want to add two polynomials, let's say I've got another polynomial which is x squared plus 2x plus 1, I can work with polynomials as such, really. Okay? So you can work with whichever is convenient for you. Well, if you went for this direction, then you've got to define your own functions to add or subtract. So let's say you want to subtract those two arrays, right? Well, first off, what you would do is, define an add function, right? So let's say you want to add two numbers, right? All you do is return a plus b. But this only works for numbers. So if I'm adding 2 and 3, I get a 5, right? Well, what happens if you pass arrays by mistake? Or that's your intention. That's what you want to do. Add 1 with a 3 and 2 with a 4. What do you get? It just concatenates them. So there's a problem. It's not a problem, but that's how Python understands vector addition. Well, to cast this as vector addition, all you have to do is take this function, right? And, call in np vectorize the function. So vectorize my add function. I get another add function. I get another function that is a vectorial add. So with that said, taking this and calling in vectorial add, I get what I want. So 1 plus 3 is a 4 and 2 plus 4 is a 6, right? This particular function could have been written in vector form without using vectorize, right? So you could have done, a for loop right here if you want to create your own vectorize add. So what I mean is this, vectorize add, you take a and b and you go on a loop, right? So for, I don't know, let's say c is your output, and at each time for k in length a, or you insert in c ak plus bk, right? You could have done this. Let's make sure this works. So I'll copy paste this, and I get an error. What is the error? It's telling me, oh, so this is not the right way to do it. The right way to do it is as such. Okay, there you go. So we have to return C, and there you go. Okay. When working with arrays in Python, you should always initialize them as none times length of a, right? Now, there's another tricky, and I wouldn't say tricky way, but you could define it as such, and at each iteration, you append. So in that case, you have a list, right? There you go. To make sure what the type is, it's a list, okay? Okay, good. This is how you vectorize functions. So this is way off easier than doing this or this, right? So if you've noticed, all this is actually NumPy. We didn't talk anything about Skippy. That's because, as we said, Skippy builds on top of NumPy. Now, let's start with Skippy functionalities. And in particular, I'm going to talk about special functions of Skippy. Right, so the first thing I'm going to start with is Airy Functions. So what are Airy Functions? They're actually two independent solutions, AI and BI, of the following differential equation. Now, they take the following forms where t is actually a function of z, where it is a function of z as such, and k sub 1 over 3 and I sub 1 over 3 are solutions to the following differential equation. So without you having to go, write some numerical methods to compute the Airy functions, well, SciPy has some functionality for this. That said, you can go ahead from SciPy and import special, that are special functions. And let's say you want to define an x-axis that starts at -15, ends up at 5, taking 201 points. Oh, and by the way, this is np.linespace, right? And you go ahead and call special.airy of x as such. Now, as you can see, there's 4 arrays, right? And they are actually the AI, AIP, BI, and BIP. What is AIP and BIP? Well, they are the derivatives of AI and BI, but we're only interested in AI and BI, right? So let's plot them and see how they look like. matplotlib.pyplot as plot for plotting. Then you call plot AI versus x in red, and give it a label of AI of x, one of the Airy functions. The other one is BI. Let's plot it in dashed blue and give it a label of BI, right? So this is how it looks like. Well, let's cut the y-axis because this guy explodes at 5. So cutting the y-axis by calling the limits. So between -0.5 and 1, this is how the function looks like. And let's give it some grid, right? And a legend so that we differentiate between the functions. Finally show to get rid of the upper message. Okay, so this is how you work with Airy functions on SciPy. You've also got the exponentially scaled Airy functions that are Airy functions, right? Scaled with some exponential. So a way to do this on SciPy is you import Airy E for exponential. Okay, now let's call some z values and call Airy E, pass it z, and as before we've got 4 functions right here. AIP, EBI, and EBIP. Okay, so let's plot on 2 subplots. Here's the empty subplots. I'm going to pass by each and every one of those 2, and I'm going to plot the first one in red, okay, and the second plot in blue, right? I'll give this subplot a legend found in data 2, which is this, right? And finally I'll give a grid as such, and I'll just show it, and there you go. So this is how you work with exponentially scaled Airy functions on SciPy. So now let's talk about Bessel functions, and Bessel functions actually solve the following differential equation called the Bessel differential equation. And Bessel functions really have a lot of applications, such as in electromagnetic waves and acoustical waves in cylindrical guide, antenna, or pipes. They also describe the modes of vibration of a thin, circular, or annular membrane. They're also used in diffraction of circular slits, as well as the study of frequency modulation in telecommunications. Okay, so the Bessel function is widely used in many applications, and that is why SciPy has decided to include it in one of its libraries. Now I'm going to explain the Bessel function using SciPy through a very common example, that is the vibrational modes of a thin drumhead. So make sure you import the special library, right? And we're going to define a function called the drumhead height that takes in two integers, a distance, an angle, and a time axis. What I'm going to return is the zeros of the integer order Bessel function. So I'll pass it the two integers, and I'll return the drumhead height that is defined by the following equation. So cosine times a shift in angle times the special Bessel function. Okay, I've got my function. Now I'll define a theta axis with steps of 2 pi and a radius with steps of 1 and an x-axis by spanning all values of the radius. Likewise, a y-axis, but this time instead of a cosine, I'll put a sine. And a z-axis that is generated using our drumhead height function. So I'll pass it r and theta. And an instance t of 0.5. And of course I want to pass through the values in the radius. Okay, all is good. Now let's do some plotting. So in case you didn't plot matplotlib, in case you didn't import matplotlib, well, you do it. Also, we'll be needing, since this is a 3D plot, we'll need the mpl toolkits.mplot3d. We'll import axis 3D. And one last thing, we're going to need the matplotlib cm. So we'll open a figure. We need the 3D axis. And then we'll surf, so plot._surface x, y, z. I'll set an r stride to 1. I'll set a c stride to 1. And I'll set a color map to rdbu_r. A vmin of -0.5 and a vmax of 0.5. And I've got an error telling me matplot, no such module. And why is that? Oh yeah, because this is a matplotlib. So I've got an error here telling me Okay, so this is a plot, sorry. And over here I've got one error telling me that argument z must be two-dimensional. The error is because my brackets here should end here. And there you go. This is how the thing looks like. Okay, so and let's label the axis. X dot set x label. Set it to x. And the same thing goes for y and z. Actually, there's a bit of an error over here. It's not an error, it's a conceptual error. So let me include Matplotlib notebook so that I can rotate my figure. As you can see, this is actually a 2D figure, it's not 3D. And the reason of this is because here I mistakenly typed in x for y. So running this, and there you go. This is how the drumhead height looks like. Looks a bit like the MATLAB logo, but it's not, because the MATLAB logo over here is all 0. Now the MATLAB logo, in case you don't know, is actually the eigenfunction of the wave equation. That's not the case here. So that's why, and this has a name. This is the drumhead height, okay? Okay, so this is one nice application of the Bessel function and how to get the job done on SciPy. You've also got the Logit function or the logistic function. So from SciPy.special, I'm going to import the Logit function. So it's as easy as evaluating any type of function. Say you want to evaluate at 2 points, there you go. And a way to plot it is really easy. So define an x-axis with 500 points, let's say, and your y is nothing other than logit of x, plot y versus x. Let me turn off this image so that this shows. There you go. Okay, looks good. And you can give some labels. There you go. This is how the logit function looks like. And it's easy as one line of code in SciPy. You've also got the gamma function that is defined as such. Well, how do you work with it? It's the same way as the logit function. Well, this time we need to import it as such. And you can define an x-axis, say from -3 till 5 with 2000 points. Y is the gamma of x. And you can go ahead and plot it, let's say in blue. This is an MP, sorry about that. And make sure you turn off this image. And there you go. Actually, we could have left it like this and just, cut off the y-axis. So plot dot y limits, you can set them between -10 and 10 as such. Actually, let's raise the max. Okay, not bad. So this is how the gamma function looks like. To make sure this is the gamma function, actually what you can do is can also import the factorial, because the factorial is actually the gamma function at natural numbers. Actually, the gamma of x is x minus 1 factorial, if you will. So let me show you what I mean. Let me plot, let's say I've got, I don't know, numbers from 1 till 7, and over here I'm going to plot the factorial of those numbers, but k minus 1. As you can see, they align onto the line. Well, since this is discrete, well, plot them as dots, right? And as you can see, here's your factorial, right? Okay, so this is how you get the gamma function on skip. You've also got error functions. So say I want to plot from minus 2 till 2 with 100 points. All you have to do is call special.error function on x, right? And make sure you turn off this image figure so that you see it over here. Anyways, there you go. And say you want to give your y label a fancy label, so you can go ahead and LaTeX it as such. Okay. Give your x label also a label. And there you go. How cool is that? Here's your error function with Skippy's ERF of special of Skippy. Okay? You've also got the entropy function defined as such, and a way to do it on Python and on Skippy is define an x-axis, then call your y as special.entr for entropy as such, and all you have to do is open a figure and plot y versus x as such. There's your entropy function. Okay, let's plot it from 0 to 1. There you go. Okay? You've also got the Huber function, really used a lot in optimization, and in particular in estimation. You can also go ahead and plot it, defining an x-axis, and your y is the Huber. Give it a particular delta, usually small, and your x values. Then you plot y versus x. And I always do this mistake. Forgive me about that. And Huber is actually from special. So special, there you go. It starts off as r squared, and then it continues as r, right? And there you go. For a small r, this is half r squared, so quadratic. And then once you exceed this, it behaves as r, right? There you go. This is really used in estimation theory. Okay. And why is that? It's because this function, although it looks disgusting, it's convex, right? It's convex. To show you, there you go. It looks like your r squared, right? Except that you've got this linear approximation on the edges once you escape your radius delta. Anyways, so that's all I have to say about special functions. Really, there's a really rich documentation on this link related to all types of special functions, such as the elliptic function that we didn't talk about. A lot of Bessel functions over here, you can find a lot. You've got the modified Bessel function, exponentially scaled Bessel function, spherical Bessel functions, as well as Riccati Bessel functions. You've got the Struve functions, along with a lot of statistical functions, such as the inverse function of the binomial and the binomial itself, the survival function, the F survival function, chi-square functions, Gaussian cumulative distribution function, the Tukey lambda functions, as well as Kolmogorov distribution, the Box-Cox transformation as well, and really a lot of functions right here, such as Legendre, as well as ellipsoidal and orthogonal polynomials, such as the Laguerre polynomial. We've got hypergeometric functions, as well as Matthew related functions, Kelvin functions, combinatorics, the Lambert function, really a lot of functions over here. So that's it for this lecture. In case you found it beneficial, please leave a like on the video, subscribe to the channel, and let me know in case you need more Skippy tutorials. Make sure you head over to my Patreon account in case you want to show support to the channel. You can donate as little as $3 on Patreon. My link is found in the description below, and I'll see you